Good, good. I have really good news that does not affect any of you, but I was supposed to have a midterm next Wednesday, and I was the kid in the class who was like, hey, I don't want to have the midterm on Monday because we have to do the homework this weekend. Can we move the midterm to Wednesday so that like we have time on Monday to ask questions about the homework? And then the professor was like, oh yeah, that makes sense. And then like 10 seconds later, my phone, because you know, we all text each other or whatever while we're paying attention to our professor's Zoom lecture. Like 10 minutes later, my phone is blowing up and everybody's like, oh, nice job, man. So one, I got my own midterm delayed 2 days, which gives me 2 extra days to study next week. And 2, I got street cred with my homies who were in the same class. Do y'all see the warm-up? Am I sharing the right screen?
Yeah.
Oh, okay, yeah. Okay. So hey, here's what we're doing today. I'm so sorry, my brain is being dumb. I'm trying to open my folder worth of notes on my other screen really quickly. Okay, item number 1, I have a basic right triangle. Please solve for B. What do we do to solve for B?
Pythagorean Theorem.
A tale as old as time. A song. Well, I mean, it's a tale as old as like 2,300 years ago. But yeah, 2,300 years ago, a really smart dude figured this stuff out. So please use the Pythagorean theorem in order to solve for side length B. And then item number 2, we're going to do a Pythagorean puzzle, which I'm fairly, I mean, it's, you know, I'm really good at using Google or whatever. But normally when we get to this section, we do a physical, actual, factual Pythagorean puzzle in class that involves, you know, cutting stuff out and scissors and all that stuff. However, we don't have to do that today because obviously we're all at home and I don't want to make you all download a thing and print it out and then cut it apart because I don't know who has access to what printers or any of that stuff. I found a digital version of the exact same puzzle that I wanted us to do. So if you would all be so kind as to go to Google Classroom where you got this link, you're going to see a posting go up right now called Pythagorean Puzzle. Please click that link and we're going to play a little game. What I would like you to do, and I just want to make sure that we're all on the same page because there are a few different versions of the puzzle. When you open it up, your screen should look like this. And there are some different partitions of the Pythagorean puzzle that will work here. I want you to choose this one right here, the second option to the right, so that your pieces are cut this way. And here's the deal. I would like you to take the colored pieces that are here, and I would like you to fit them here. So like I said, on your Pythagorean puzzle page, choose the second partition, choose this partition right here, and you should be able to grab these pieces and move them around, or I don't know if you're fancy, but my laptop is also a touch screen, so I can just like touch the screen and get my greasy fingerprints all over it. You want to grab those pieces and you want to move them over to the right so that they all fit. Take about 2 minutes and both, stock prices, and both do the warm-up, solve for the missing side of that right triangle, and go to that Pythagorean puzzle and see if you can solve it. After a few minutes, we'll go over both of these together, and then we'll get going with notes for today. Today, we're going to talk about the Pythagorean theorem, which, of course, you know, we all know how to do. We've literally been doing it probably since like 6th grade. We're just going to flesh it out a little bit more today. How's it going out there?
Pretty good.
Yeah.
Nah.
Have y'all been trying to keep busy, develop any new hobbies?
I kind
Yeah,
of got
sort of.
had like a mental breakdown the other day.
The good kind or the bad kind?
I don't know. It can be interpreted in many ways.
Wise, actually very wise for a freshman. Yeah, I mean, sometimes you have a mental breakdown and it just like ruins everything and you have a bad time. Other times you have a mental breakdown and it causes you to reassess your goals and then you rebuild yourself differently. But sometimes that's just like necessary for growing up. Sorry, somebody else out there have a comment? No? Anybody else? You guys doing okay out there?
Yeah, not bad.
Who's been exercising? Have you all been trying to stay fit?
I'm swimming.
That's awesome that you have a pool. Everybody who doesn't have a pool, including myself, is very jealous.
Yeah.
I tried, but it's too cold.
Well, I'm
Oh, I mean,
I genuinely wish I had a pool. Like, I don't care if it's cold or not. I would have just swam the whole time.
How? How are you gonna swim whenever it's like freezing?
freezing.
I've been on
is
swim team all my
32
life,
degrees.
so I'm used to it.
Yeah, I mean, usually like swimming in cold water only sucks for like the first minute, and if you like go into it slowly, you'll never get there. But it's just like going running on a cold day. Like the exercise itself will keep you warm from the inside. So, as long as it's like cold without being dangerous cold, just jump in and get moving. And after you get moving, you'll be warm.
It'll it'll go away. Cool.
Yeah.
Yeah.
You warm up internally from the effort.
And also, like, during swim practice, they don't let us swim in hot water because they say, like, if you swim in hot water, you're just going to relax too quickly. So they always, like, make the pool really cold.
Yeah, it can be dangerous to swim in water that's too hot because of the way that heat engines work. Nonetheless, interesting stuff. We own our own house now, so like we don't have a pool. But at the first place that me and my wife were renting together, that place had a pool. Having a pool was awesome. It's just such a convenience in LA. Nonetheless,
Mr. Robinson?
yeah.
I think I got the puzzle.
Yeah, I did it too.
Yeah. We'll go over it together. Yeah.
Looks like the Microsoft logo.
I downloaded the Nike Training Club app and I do it every day now.
Tight. Yeah. Nike Training Club is what's up. Actually, let me, if you guys are doing Nike Training Club or Nike Run Club, you can add me. Let me pull up my little name or whatever. It's so dumb, but it's so fun. I have one other person in my graduate department who's like me, I guess, somebody else who runs long distance. And let me see how to add friends on here real quick.
Mr. Robinson, I have a random question.
Yeah.
You know how to do a flip?
How to what?
Do a flip, like front flip, back flip?
No. I've always been too afraid to do that. I could do a kick flip, but I can't flip my whole body.
I'm trying to learn a front flip.
Oh, okay. Yeah. So if you have a Nike Run Club or a Nike Training Club, you can add me by just using my personal email. So if you add to your contacts eric.ma.robinson@gmail.com, it will add me on your friends list on there. And here's why it's fun. It's so dumb, but I love it. Whenever I go running, if one of my homies on my friends list notices, it gives a little pop-up notification. And it's like, your friend Eric Robinson is currently on a run. Do you want to cheer them on? And if you tap cheer them on, while I'm running on my phone, it'll give me a pop-up. And it's like, hey, your homie Bhavna says, good job for doing an exercise today. It's only just so that you can cheer on your friends while they exercise. It's dumb, but it's some dumb fun.
I added you.
Tight.
Nike Training Club.
Awesome. Yeah. Anybody else out there with Nike Training Club or Nike Run Club, add it and cheer each other on in these hard times. Nonetheless, let's go ahead and get started with item number 1. How do we solve for B, y'all?
We can do 52 squared plus b squared equals 173 squared.
That is correct. And then these are big numbers, so we'll go ahead and rely on calculate. So that'll be 173 squared. We also need to know 52 squared. So that's going to be 2704 plus b squared is equal to 29929. And now how do I get b alone?
Subtract 2704.
From both.
Yep, subtract 2704 from both sides, and that tells us that b squared is going to be equal to 27225, or 27,225. And how do we get b alone?
Square root.
Square root it.
So b must be equal to the square root of 27225. b is equal to?
165.
Yep. And what I'm about to say isn't always true, though it is usually. You have a pretty good indicator that if you have a big nasty number and you're going to take its square root, there's a strong chance that it's going to work out cleanly and end in 5 if the final two digits here happen to be 25. Really common, because when you square out 5, it becomes 25. Just a thing to look out for. So yeah, b has to be equal to 165, which means that this is a special case where this side length works out to an integer. It won't always be an integer. This is a special case. This is a Pythagorean triple. Is this okay?
Yeah.
Okay. And now let's go to the puzzle. Nope, not that. Nope, not that. Oh, I think I closed it, but luckily I have it in Google Classroom. Derp, 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 derp. Oh, by the way, I was not looking at those stocks for my own benefit. In calculus, we're working on a business assignment right now, so we were talking about stock prices. Hey, anyway. So this partitioning, the only reason why I want you guys to do this one is that the print out puzzle that I did at home, this is the version that we would have used in class if we were all, you know, hanging out together in Pasadena in the same classroom. But I'm going to go ahead and show y'all how to solve it now. And just a little bit of information about how this is cut. Notice the way that this is done, you're like, well, how would you know to cut it that way, right? This line is parallel to the top line of the rectangle that's going to receive it. And this line is parallel to this side of the rectangle that's going to receive it. And fun fact, it actually doesn't matter exactly where you place these cuts, as long as they are parallel to the receiving rectangle. It will always work out no matter what. So I'm going to take this, and here's how we remember, or here's the easiest way to follow along with the solution. Each one of these 4 corners is a 90-degree angle, right?
Yeah.
Yeah?
Mm-hmm.
And because each one of those is a 90-degree angle, those are actually the corners of the receiving square.
My teacher's doing like a warm-up right now. Did you figure out how to do it? Yeah. Oh.
Autos.
Wait, which one's the boss? The white one?
Autos.
Autos, you're not
Autos.
muted.
Not muted.
Autos did not muted for us.
Autos, you're not muted.
I think he probably muted the class, which is why he can't hear you trying to warn him.
Oh,
Rest in
no.
peace. Rest in peace.
So I guess the easiest way to deal with that is participation points or something.
Ooh.
But that's a bummer. I don't want to have to do that. I'll be real with y'all. Like, we're supposed to have you guys leave your cameras on so that we can tell that you're paying attention. I don't like that. I just think that that's weird. Because like when I attend my online classes, I don't have my camera on. But yeah, like you need to be aware and keep your microphone muted. And if you're not paying attention, we notice and all that bad stuff. But once you get all the pieces to fit together, it'll give you a pop-up that's like, hey, you're a smarty smart. Great job, smarty. But the interesting thing is not just like that this works. What is the point of this? What does this puzzle have to do with the Pythagorean theorem? Does anybody want to take a crack at this?
They all are like triangles, kind of.
Where is the triangle that we are talking about?
In the middle.
The triangle that we're talking about is actually here in the middle, and each one of these is a square. So this side length of the square is A. So what area is that square to the left?
Wait.
A. A.
It's actually
squared.
A squared, because it's A times A.
Oh, so-
Similarly, this area down here is
B squared.
B squared. And the whole point of the puzzle to show that if you make the correct cuts and you move the pieces over, they add up. And what does that tell us?
C squared.
That
That's
the
C.
area of A and the area of B are added up to get the area of C.
That is very good and precise. Yes. That the total area of C squared is precisely equal to what you get if you take the areas of A and B and you add them up. And if you want to fiddle around with this more, it's just like good brain stuff, because I can already tell that y'all out there like video games, and this is a video game, right? That no matter how you cut it, it will always work out. You should give it a shot. Try some of the other versions of the puzzle.
Yeah, I accidentally did this one.
Huh?
I accidentally did this one in the beginning.
Yeah, same.
Yeah, same.
Oh, that's fine. That's cool. Did it work out?
Yeah.
Yeah. The blue goes like on top,
Yeah.
right?
It was pretty.
Yeah, it works.
Blue goes
I
top,
did this
right?
one too.
Yeah, it's pretty simple.
Blue goes top right like this,
Yeah, yeah.
and then
Yep.
what?
And then the
Yeah, I did it differently.
green goes to the
I
left.
did it differently.
Yeah, the green goes top left.
Yeah,
There's
and
different
then
ways to do it.
the purple is all the way in the bottom right. And then the red is right above it. No, the other way. Yeah,
Yeah, and then the red right up top.
Oh, I did it a different way.
this is how I
But
did
it
it.
still worked out?
Yeah.
Yeah.
Tight? Cool.
Yeah, a lot of ways work.
But yeah, so depending on how you cut it, that doesn't change the area, right? So no matter what, so long as you have something where you will have 90-degree corners to fit into the edges of the square, this will always work out and show that the total areas A squared and B squared are equal to the area of C squared. This is the like fundamental underpinning of why the Pythagorean theorem works. So it's basically our notes. Let's go ahead and notate that, and then we'll look at some questions, yeah? Okay, so today we're going to talk about section 8.2. Today we are talking about the Pythagorean theorem again. And I apologize, Pythagorean is a name. It should always be capitalized because it's named after Pythagoras. Okay, so the Pythagorean theorem has been drilled into us since elementary school. It is the simple statement that c squared is equal to the sum of a squared and b squared. But what we just learned by fiddling with that digital version of the Pythagorean puzzle is we learned that this is actually a statement of areas. This is to say that in the special case that I have a right triangle, and A and B are my two short sides, and C is my long side. And what is the name of the long side of a right triangle?
Hypotenuse.
Yep, the hypotenuse, which I'm gonna go ahead and notate here. Hypotenuse is always the longest side of a right triangle.
Because it's the opposite from the 90-degree angle, and that's the biggest.
Yes, yeah, we had that theorem before when we were doing inequalities for triangles, that yes, the biggest side is opposite the biggest angle, so this is the biggest angle, therefore the opposite side is biggest, yeah. That this guy here is actually a statement of areas. That's why it is squared and not just some other mathematical object. It's not times a number, it's not subtracted. It is a statement of areas. So this is to say that if I were to take and I were to say, well, this is my A and this is my B and this is my C, that if I take this length and I square it, which is to get, you know, the square area in here, well, this is A squared. And if I were to take this bottom side here and I were to square it, which I guess I wrote that definition of hypotenuse way too close, huh? Rip in peace. Then this space here is going to be equal to B squared. That if I take these two areas and I smush them together, it is exactly the same area as a square, which is made of the hypotenuse's side length. So this guy here is C squared. And what we just saw is that if we take this A and we fit it in here, that would be our A squared, that we can fill up the rest of this space with cuts of B as long as we do those cuts correctly. So this C squared, this total area, this C squared, is actually equal to the A squared piece that we put in the middle, and B squared over 4, B squared over 4, B squared over 4, B squared over 4. Or each one of these is 1/4 of B squared. And if we add up 4 sets of 1/4, this in total is just B squared. This is where the Pythagorean theorem comes from. Is that okay?
Yeah.
Yeah, I guess it's okay, except for the part where this is ugly because of the overlap. I apologize. Do your notes prettier than mine. Some notes. If all 3 sides of a right triangle are integers, we call that set of numbers a Pythagorean triple. And what's the most famous Pythagorean triple that we end up using a lot?
3, 4, 5.
Yup, 3 and 4 and 5. And this works out because 3 squared plus 4 squared is equal to 5 squared, because 9 and 16 is equal to 25. However, here is a little bit of additional information about Pythagorean triples. Number 1, if a set of digits is a Pythagorean triple, any multiple of that set of digits is also a Pythagorean triple, because it is describing a triangle which has the same geometry as the original, just bigger, right? That is to say, it makes a similar right triangle. So if 3, 4, 5 is a right triangle, if I wanted to multiply this all by a constant, let's say my first digit is now 9, what are these other digits going to be?
12, 15.
And this is describing 2 similar right triangles, different by a scale factor of 3. But does changing the scale factor of 2 similar polygons, does that change their angles?
No.
Nope.
No, we know that similar figures, that doesn't change their angle. To scale it, to dilate it and make it bigger. And because it doesn't change the angles, it can't change that 90-degree angle. And if it can't change that 90-degree angle, it's still a right triangle. And if it's still a right triangle, the Pythagorean theorem still applies. So we can show that 9 squared plus 12 squared is equal to 15 squared. So 81 plus 144 should be equal to 225, I think. And yeah, if you take these two and you add them together, this shows that 225 is equal to 225. So not only are Pythagorean triples good, but any multiple of a Pythagorean triple is also a Pythagorean triple.
So you can multiply the Pythagorean triple each one by 1,000 and it'll still be a Pythagorean triple.
You could multiply it by 1,000. You could multiply it by 257. Yeah, any scalar multiple of a Pythagorean triple will remain a Pythagorean triple.
So in reality, technically, there's only one Pythagorean triple, but it's only affected by a scale factor.
I love that question. No, there's an infinite number of unique Pythagorean triples, but from one Pythagorean triple, because you could multiply it by literally any number you want, there's an infinite number of versions of 3, 4, 5. But I would argue that if you took another Pythagorean triple, the other common one that we like is 5, 12, 13. 3, 4, 5 and 5, 12, 13 are different, but each one of them could give rise to an infinite number of Pythagorean triples. It's a really good question. Okay, so let me go ahead and show y'all that Pythagorean triples might be a common idea, but it is actually still an active field of research for mathematicians. If you look at the Pythagorean triple page on Wikipedia, you get a nice little breakdown, and they have the little animation in the top right of how it is that a squared and b squared fit together nicely into c squared. I actually really like that GIF. Do y'all see that playing in the top right?
Yeah.
But the way in which more Pythagorean triples are obtained is by using scatter plots and really fancy mathematical methods. So what you're looking at in this crazy grid, right, is as we go out to the right, that's our A length. As we go upwards, that's a B length. And if you think about C, right, the hypotenuse, you could say that, well, if I wanted to position all possible hypotenuses, I would make a circle of a radius equal to that hypotenuse. So if I wanted to do 3, 4, 5, if I wanted to look for that Pythagorean triple in this kind of scatter plot, what we would do is we would go to Desmos, and I would say, I'm going to use the equation of a circle, right? And I don't know if you guys know, but the equation of a circle is x squared plus y squared. And if I say that this is equal to my radius squared, it'll draw us a circle. So I'm going to go ahead and say that this is equal to 5 squared. And check this out, right? I've drawn a circle here of radius 5. Look at this point. What point is that?
.99 and 4.007.
3, 4.
Right there, 3, 4. So what this is saying is that the radius from 0 out to this point, that's 5, and that occurs at the coordinate 3, 4. This is one way that you can use circles in order to find possible Pythagorean triples. You draw a circle and you see if the circle passes through any perfect coordinates. This version of it is just that same idea, but instead of drawing a circle that's radius 5, they drew every circle possible between the radius of 1 and the radius of 6,000, and then a computer automatically looks for the points that are perfectly on integer values. Those integer values are Pythagorean triples. And so 3, 4, 5, 5, 12, 13, these are probably the 2 that you should memorize. And also 7, 24, 25, just because those are the 3 that I've seen appear a bunch on the SAT once they start giving SAT tests again, right? But yo, there are so many more than that, and there's so much complex mathematics that can be used to determine additional Pythagorean triples. Is that okay?
Yeah.
Okay. Let me give y'all 2 more notes, and then we'll do an example question similar to something that we've done before. You should also note that the Pythagorean theorem can be used to determine angles. And here is the logic of this. If a squared plus b squared is equal to c squared, if you know all 3 side lengths and you can check it against this and it works out, we can make the conclusion that therefore angle C is equal to exactly 90 degrees. Or if you take the 3 side lengths of a triangle and you do a squared plus b squared, and it turns out that that is not equal to c squared, then therefore we know that angle C is not equal to 90 degrees. The Pythagorean theorem itself is basically a conditional statement. The Pythagorean theorem is saying that, like, hey, if it is a right triangle, if you have one 90-degree angle, then a squared plus b squared is equal to c squared. This is saying the reverse of that, that if you have the three side lengths, you can then use the Pythagorean theorem to check whether or not you're talking about a right triangle at all. So for example, let's say that I have a triangle. A triangle has side lengths 73, 55, and 49. Is it a right triangle? To figure out whether or not this constitutes a right triangle is a simple matter of applying the Pythagorean theorem. So tell me what to write, so I can make sure that we're all paying attention and, you know, not playing video games.
Well, you would write 49 squared plus 55 squared equals 73 squared.
So 49 squared plus 55 squared is equal to 73 squared. And if this gives us back a true statement, then it is a right triangle. So on the left, I'm going to do 49 squared plus 55 squared. On the left-hand side, that gives us 5,426. And on the right-hand side, we're comparing this to 73 squared, which is 5,329. Are these numbers equal? The easiest question I've asked all day.
No.
No.
No. So therefore, this is not a right triangle. Now, don't get me wrong. We will have a way later to solve for the angles of any triangle. But for right now, all that we know is that the Pythagorean theorem can basically tell us whether or not a single angle is 90 degrees. But before the end of this chapter, we will have the mathematical fortitude, the ability to solve for all angles of every triangle.
From this, are we able to tell if it's acute or obtuse?
You can, based on which side is bigger. So because the side with the hypotenuse is smaller, that tells us that this is implicitly an acute triangle. If the side with the hypotenuse was bigger, then that would tell us that we are talking about an obtuse triangle. It's a good question with a good answer, but it's not something I'm going to test on.
Okay.
So you could say that, quick side note, a squared plus b squared less than c squared. This is telling you that this is an acute triangle. But if a squared plus b squared is greater than c squared, then this is, oh crikey, hold on, give me 1 second. My brain is dumb. Nope, got it backwards. Sorry, if the hypotenuse squared is bigger, if the hypotenuse side is bigger, it's an obtuse triangle. If the hypotenuse side is smaller, then it's an acute triangle.
Okay.
Excellent question. And it's not that big of a deal to me because instead of just knowing what category the angles fall under, by the end of the chapter, we'll just be able to calculate them directly.
Oh, Mr. Robinson, if we're not given a model of a triangle, but we're given the numbers, like we're given 49, 55, 73, for example, could we still solve for the other angles, or we would have to have the model to figure out if it was adjacent or opposite?
That's an interesting question. If it was a shape that wasn't a triangle, you would be out of luck and you would have to do some doing in order to get the answer. But there's only one set of angles for any set of sides of a triangle. Because if you were to go 49, 55, 73, or swap two of the sides and say 49, 73, 55, every side is still connected to every other side. So no matter what, you either get this triangle or its mirror image. And in both cases, the angles are identical.
Oh, so you could still, for example, like if you try doing like the cosine with the values that we have right now, but if we did it with a different value that was flipped, could it still work?
We will talk about sine, cosine, and tangent on Monday. And it's important to keep in mind that if you're using sine, cosine, and tangent alone, they only apply to right triangles. We just showed that this is not a right triangle, so sine, cosine, and tangent would not be enough to solve for its angles. However, by the end of the chapter, we will have techniques that let us get the angles, even of triangles like this.
Yeah. Would it be like
Okay.
the inverse?
I will talk about that when we get there. Okay, so I'm now also going to talk about one more thing, and then we're going to do examples for the rest of the hour. And this is a thing that is going to be weird and maybe a little bit confusing. If you have partial lengths, you can use the Pythagorean theorem even on oblique triangles. However, this set of notes that I'm about to do is going to be incomplete. We're not going to finish it till the end of the chapter. I just want to make sure that you guys have a little bit of a preview of this idea, a little bit of flavor, so that when I hit you with these notes on next Thursday, they don't blindside you. Oblique triangles, just as a definition, are all triangles which are not right. Just by definition, oblique triangles are a category of omission. So if you take all of the triangles that can exist and you remove all of the right triangles, what you're left with is all of the oblique triangles. Now, oblique triangles technically cannot be treated with the Pythagorean theorem. However, and this is a trick that we're going to be using a lot in our notes, every oblique triangle can be treated as two right triangles if we do what? What were we talking about last section? What kind of
Pull down an
were we adding?
altitude.
Exactly.
Altitude.
We're going to throw down an altitude on the inside. So every oblique triangle can be treated as two right triangles with the addition of an altitude, which gives us some mathematical freedom. So let's go ahead and get crazy. So I'm going to draw now an oblique triangle. And again, this is not a right triangle, which is to say this ain't 90 degrees. But nonetheless, I'm going to call some lengths out here. This is going to be A, this is going to be B, and this is going to be C. Now, it would be wrong to say in this case that A squared plus B squared equaled C squared. That's not true, because this is not a right triangle. But I'm going to slam down an altitude, and I'm going to give it a value. I'm going to say that this altitude is H, just because normally altitude is talking about height, so this is kind of traditional. And now I'm also going to take C, and I'm going to split it up. I'm going to break it into this piece that goes from here to here. I'm going to call this X. So logically, what does this have to be?
C minus X.
C minus X.
That is what's up. So the whole length on the bottom of the triangle here, this whole thing is C minus X. I'm sorry, this whole thing is C. So if this little piece is X, this has to be C minus X, so that if I add them back together, C minus X plus X gives us back the grand total length, which is C. Let me label that a little bit more clearly on there, because I don't think it's obvious that C is talking about the total length. C is talking about the total length, C. So now let's do the Pythagorean theorem. However, it's not going to be enough to do it once. We'll have to do it twice. So let's go ahead and do the Pythagorean theorem for the left-hand side. What does the Pythagorean theorem look like for this?
H
H
squared.
squared plus X squared equals A squared.
So for the left-hand side, we can say that A squared plus X, X squared plus H squared is equal to A squared. Because on the left-hand side, A is the hypotenuse. And what about on the right-hand side?
H squared plus C minus X squared equals B squared.
Okay? And so, even though this is not a right triangle, because any oblique triangle can be split up into two right triangles as long as we toss in an altitude, we could now do treatments for this triangle using the information here. By adding in that altitude, we're turning it into two right triangles that have some common terms. What is the common term that is present on both equations, which is not actually a side length of the triangle?
H squared.
H squared.
H squared, yeah. So I'm gonna go ahead and I'm gonna solve for it and substitute it so that we can get a new equation that doesn't have H in it at all. So on the left-hand side, how can I solve for H?
Subtract x squared from both sides.
H squared must be equal to a squared minus x squared. And because this is a redefinition of H, I can now take this new definition of H and I can plug it in here for H. Here's what our equation becomes. We now get, after substitution,
Well, there's a proof.
we get a squared minus x squared, that's our new definition of H, plus c minus x squared. This is equal to b squared. Is this okay?
Yep.
Yeah?
Yeah.
And now the last thing that we can do is we can do c minus x squared to expand that out just a little bit, and then we'll have a new reusage of the Pythagorean theorem, which will hold true even for this nasty oblique triangle. The question is, what is c minus x squared?
C squared minus x squared.
And it's really important that you understand
Oh wait, no, it's not. It's
that
a
that is
quadratic.
not true. It is really important that you appreciate that that is not true. Here's the deal. C minus x squared, when you take something and you square it, what are you actually doing?
Applying it by itself.
Yeah.
So c minus x squared is actually c minus x times c minus x. And what's the rule about multiplying two binomials?
You do FOIL.
FOIL. So this is actually going to give us c squared minus cx plus x squared, which is the same as c squared minus 2cx plus x squared. So if we do this as our final approach on what is happening here, I'm going to substitute this in for c minus x quantity squared, and we get a squared minus x squared plus c squared minus 2cx plus x squared is equal to b squared. And what cancels?
X squared.
X squared is here and it's positive, x squared is here and it's negative. So both of those cancel out, which I think is pretty nifty from a math perspective. And so here's what this new version tells us for this oblique triangle. A squared plus c squared minus 2cx is equal to b squared. We still get some kind of equation that will work here. The only extra information that we need is x. If we knew what x was, we could do any calculation that we needed to using this relationship. So the Pythagorean theorem yes?
So does this work for all oblique triangles?
As long as you have a way to get x, yes. And this equation has its own name, but we're going to come back to this, like I said, next week on Thursday and do this derivation again once we know information about a good way that we could get x. I just wanted this as a quick algebra exercise because it's kind of pretty the way that it works out when the x squareds cancel. Is this okay?
Yeah.
Okay. Now I got 2 questions for you, and then we'll call it a day. I'll post the homework, and then of course that means tomorrow when y'all come in, we'll have that entire period to work on the current homework assignment.
Is our homework assignment gonna include what we just did, or no? That's like Thursdays.
No, that the whole point of that is just so that we have a preview of what some of our notes will look like next week, just because seeing it now will make it easier when you see it again next week.
Okay.
Okay. Item number 1, I have a rectangle with one side length of 50 and a diagonal length of 130. Please figure out what is the perimeter of this rectangle. And then item number 2, please solve for A, where our hypotenuse is 10 root 2, and this other short length here is 7 root 3. Oh, and I actually, you know, the numbers don't change. I drew it wrong though, because 7 root 3 is actually the longer side of this. So this is A. This is 7 root 3. You don't have to change your numbers if you don't want. Okay, so item number 1, how do I find the perimeter of this rectangle?
The Pythagorean theorem.
Yeah, and the deal here is that the Pythagorean theorem doesn't just apply in right triangles. It'll apply in basically any shape where a right angle can be defined somehow, which is to say some of your Pythagorean theorem homework is going to have rectangles. What are some other shapes that have right angles built into them?
Squares.
Squares, what else?
Correct. Parallelograms.
Parallelograms of certain classes, yeah, so every rhombus has a right angle right in the middle of it. Also kites. I'm a big fan of kites. Actually, tomorrow's warm-up will be a kite question, just because kite questions are real fancy. So nonetheless, we are going to use the Pythagorean theorem to solve for whatever this length is here. I'll just call it x. And so what did y'all get out there for x?
120.
130 squared is going to be equal to 50 squared plus x squared. And if you do the math to solve for x, that'll be 130 squared minus 50 squared. Then square rooted will give you x. And yeah, x is 120. So that means that 50, 120, 130 is a
Pythagorean triple.
Triple.
Yep. And so this side here is 120. And how do we get the perimeter?
You add all the sides up, so 50, 50, 120, 120, so 340.
Very good. Keep in mind, opposite sides of a triangle are equal. If this guy's 50, this guy's 50. If this guy's 120, this guy's also 120. And so, yeah, the perimeter is 340. And then item number 2, let's solve for A. Again, it's just the Pythagorean theorem, so it's going to be 10 root 2 squared plus 7 root 3 squared. Oh, ooh, made a mistake. I meant equals. I think I said equals, but I wrote a plus, huh? Plus a squared. So here's why I wanted to go over this. What is 10 root 2 squared?
10 root 4.
20. So it's 10 times 2. Won't the root go away? Or it will also.
Okay, and that's why I bring this up. When you square something that has a root in it, we need to square both of the terms that are being multiplied. So 10
It's 200.
squared, 10 squared is 100.
And then times 2.
Times 2, which you can think about this two ways. It's either root 4, because it's squaring the 2 inside, and then the square root of 4 is 2. That works. Or just as a law, the square of something square rooted or the square root of something squared, those two things destroy each other, leaving just the number. So yeah, this will be 100 times 2 is equal to, and then what's 7 squared?
49 times 3, which is 147.
49 times 3, because again, it'll be the square root of 9, which is 3, or you can just think of them as canceling. It'll be 49 times 3 plus a squared. So this is going to be equal to 200, which is equal to
147 plus a squared.
And then from both sides, we'll subtract 147.
53.
53 is equal to a squared. So
And
a must be equal to root 53. Which, is that prime?
Yeah.
Yeah.
You can't simplify it. I don't think so.
Yeah, and also we're at home, so I'm lazy and I got this going on. Is 53 prime? I love Google. It's just yes, just a real simple, just yes. And of course that means it has no multiples, so therefore it cannot be simplified. Anyway, that's it for today. I'm gonna go ahead and I'm gonna post 2 pages of practice because you can never get enough Pythagorean theorem practice. And when we come in tomorrow, it's already Friday, we'll have time to work on those 2 homework assignments. I'll read out the solutions to them during our work time, probably towards the end, so that you can check your answers. And that'll be it for the week. Are there any questions on what we did today?
Nope.
No? Okay. You all have a very nice day. Those of you paying attention and listening. And I will see you all tomorrow.
Bye.
Hey, see you, Mr. Robinson.
Bye, Mr. Robinson.
Bye, Mr. Robinson.